Good morning, everyone. Welcome back. Thank you for joining us. I'm Steve.
And I'm Scott.
Together, we're Backyard Musings, the Science and Technology channel.
Yep. And I am in Apple Valley, and Steve, I believe, is still in the semi-secret bunker. Even people with him don't even know that it's a secret bunker.
That's right.
And we're talking some quantum stuff today. So here we go.
As a reminder, we're doing one per day, 7 a.m. every day between Christmas and New Year's. So here we go. Our research team has discovered a unique quantum state at the interface between organic materials and two-dimensional semiconductors. Kind of reminds you of a Terminator. Faster, more efficient, and more adaptable technologies are widely seen as essential for the future of energy generation and information processing. Achieving these goals, however, requires new ways of understanding how materials behave at the smallest scales. An international research team from the Universities of Göttingen, Marburg, Humboldt University of Berlin in Germany, and the University of Graz in Austria has now reported a significant advance in this area. Would you like to know more?
The researchers brought together two classes of materials that have attracted intense interest in recent years: organic semiconductors and two-dimensional semiconductors. By examining how this combined system responds to light using photoelectron spectroscopy, together with many-body perturbation theory, they were able to probe ultra-fast processes at the boundary between the two materials. These measurements capture events that unfold within 1/quadrillionth of a second. That's pretty quick. Pretty quick. Offering a direct view of microscopic energy transfer. And why do we need this?
Make everything go faster.
Okay.
Right? I want it now.
I want it before it happens.
This unique blend of material properties could open the door to new technologies, including more efficient solar cells. The findings were published in Nature Physics on October 29, 2025. To carry out the study, the team relied on a specialized technique known as momentum microscopy, an advanced form of photoelectron spectroscopy. This method allowed them to track changes in the electronic structure of the materials as light interacts with them in real time.
You know, you need to, these words that my tongue doesn't seem to want to pronounce, you need to do those words ahead of time so I can get them right. So anyway, the data can be viewed as a movie that reveals how excitons, quantum mechanical particles consisting of an electron bound to an electron hole, are hole as an HOLE, are created by light and then evolve into different types of exciton states.
Sounds like the dingleberry of electrons is what it sounds like.
Okay.
By identifying the distinct spectroscopic signatures associated with each exciton type and comparing them with detailed theoretical models of the exciton landscape, the researchers were able to follow how energy moves across the 2D organic interface. One key result showed that when a photon is absorbed by the two-dimensional material, energy can be transferred to the organic layer in less than 1/10 trillionth of a second. That's 10 to the minus 13th.
That's pretty fast.
Yeah.
Okay, this is a quote. The key to this ultra-fast energy transfer is the formation of hybrid excitons, for which we now have found a telltale experimental signature, explains Professor Stefan Matthias, University of Göttingen. I'm going to assume that's in Germany, right?
Mm-hmm.
What exactly are hybrid excitons, you ask? And I do. I ask that.
Excitons are created by light absorption in semiconductors and thus play a central role in optoelectronic devices such as solar cells and light-emitting diodes. Depending on the material, excitons exhibit very different properties. In organic semiconductors, excitons are typically immobile. They are very much stuck in one place, whereas excitons in two-dimensional semiconductors are extremely mobile, freely floating all over the material.
There will be a test at the end of this segment here. At the interface of an organic and a 2D semiconductor, however, both the material properties and those of excitons might hybridize, potentially leading to the formation of a new hybrid excitons. This is exactly what the research observed at the interface of the 2D material, and I have no idea what this is. WS to the second power or squared? Not squared, because that would be above. What is that?
I think it's a chemical compound. W, I really don't know, but Se2,
Okay.
that's another compound.
Yeah. So W capital, S capital, E lowercase 2, and the organic semiconductor PTCDA.
Quote, our results allow us to better understand and efficiently harness the fundamental processes behind energy and charge transfer in semiconductor nanostructures. Nanostructures are tiny little guys. This is a crucial step towards the development of efficient solar cells, ultra-fast optoelectronic components, and novel applications in quantum technology, explains Wibke Benecke, University of Göttingen, and first author of the study, before adding, quote, as we mark the 100th anniversary of the development of quantum mechanics, our findings powerfully illustrate its relevance today for the technology of the future. So that's cool. Faster transfer of power. Combine them with those cubes that we talked about the other day, and totally it's going to be fast.
So fast, I already heard it. Yeah, this is, I don't know, where's it going to end?
Hopefully it just keeps improving, you know.
This is going to help with what all kinds of stuff, right? Communications and
Yep, definitely.
Computers. Yeah, pretty fascinating. So, okay, well, I heard it here first, folks. I don't know about you guys, but I heard it here first.
We'll catch you tomorrow. Thanks for joining us.
Take care, everyone. Thanks.